The last couple of days, we've been talking about the Tidyverse. And specifically, we've mostly been talking about the dplyr package, which includes core operations or verbs, as we called them, for manipulating data. So let's go ahead and load that now and do a little bit of review. So here are what I would consider the 5 core verbs. So there's filter, which is for subsetting rows. There's select, which is for subsetting columns. There's mutate for creating new columns. Summarize, we learned, which maps whole columns down to a single number. And arrange, which is for sorting rows based on values that they might have in particular columns. We also learned about the group by function, which can be used in conjunction with the other functions, particularly summarize. So we didn't talk about how it can be used in conjunction with the others, although it can, but in particular, it's very often coupled with summarize. All right, so let's start with a review exercise to get a little practice. So suppose we want to get a feel for the iris data set, which contains data about 150 flowers of 3 different species. And in particular, we want to know which species has the longest petals on average. So we can do that with some of the operations that we've learned how to perform already. And I'll give you a couple of minutes to work on that. So the goal is to produce this data frame, which contains the average petal length for each of the 3 species of flower. Okay, I only have one submission here. I'll go ahead and share that. That's okay. So hopefully other folks were getting quite close. All right, so let's walk through this. I'll use this as an example. So we start with the iris data frame, and we pipe that into the group by function, because what we're trying to do here is group on this factor variable, which tells us the species of the flower. And then we summarize in order to contract each of those new data frames that we'll create. So there'll be 3 of them. Each of those sub data frames, we want to contract the petal.length column down to a single number by averaging it. So yeah, so this is exactly what we want to do. This actually might be character for character, the same as what I had prepared here. So we can run that just to check that it did what we expect. And sure enough, that's exactly what we've got here. I also added this arrange computation, because even though you get the right value, without that, it happens that the species order corresponds to the petal length order. But if you wanted to make sure it was in increasing order of average petal length, you would need to include an extra arrange operation, which we can just tack on with one more pipe, showing how it's kind of nice how we don't have to think of new names for things. We can just perform an additional operation by just including it like this. If you weren't able to find the pipe function, or if your R session was not able to find the pipe function, that's because it's part of the Tidyverse, which gets loaded up here. Okay, so I just want to make an aside before we go on with the R stuff about the relationship between dplyr and what it's doing here and what you'll see in other languages and other environments. So if you're going to be using Python, I think this course is still useful, because you'll learn a lot of ideas that you can then learn how to translate into Python in a clean way, and you can sort of use the same underlying knowledge in different sort of surface manifestations. And just so that you can get a sense of kind of what this looks like, here are 3 different examples of the same calculation. So this specific calculation was designed to include all of the verbs once, including the group by operation with summarize here. And this is performing the exact same computation. So this one is in R, as you'll recognize from the funky pipe. This one is in Python, and you can see there's no pipe, but you can kind of put these dots like this. So it's fairly similar. It's different enough, but you can kind of see, if you look line by line, the similarities between these things. This one is in Julia, and you can see there is a pipe here, but then there's also this underscore stuff, so it's different as well. So each of these has kind of their own little bit different way to do things, but they're all very much reflecting the same core operations that you would use to perform this particular operation. So just to give everyone a chance to kind of weigh in. So which of those code snippets would you say is the most aesthetically pleasing to you just to look at as printed code? So there are, of course, no right answers here. All right, so it's pretty unanimous here. Let me summarize the block so everyone can see what folks said. Yeah, I agree. This is very much our strength. It's able to take advantage of the non-standard evaluation that we've talked about before, where our functions are able to consume your code and not just the values returned by those expressions. And therefore they can do some nice things. Like in Julia, you have to put this @ sign in order to consume an expression as code. So that kind of clutters things up a bit. And in Python, it goes all the way is to put these whole things in strings. So you're basically using you're trying to emulate a little language inside of the language here. So that's a bit funky. That's a consequence of the fact that Python has no ability for the language to look at the code that you've written, only to look at the values returned by that code. So in any case, I just wanted you to get a sense of the kind of universality of these things and what they look like in different programming environments. I will say that the mindset you want to have, at least in my opinion, is not, I'm going to do everything in R forever. There are going to be other situations where you're going to want to use a different, either programming language or a different environment that you might be operating in. And what you want to do is quickly learn how to do these 5 basic operations. And then once you've got that's kind of a building block where you can do most of the things that you want to do just fine. And other stuff on top of that will just be extra benefit. But you should be able to basically get around with those core operations. So this is true for things like Julia and Python and R, which ultimately are quite similar to each other. There's also SQL, which we've referred to before, which is the way that people extract data from a relational database. And Excel is also its own data science tool, much more popular as a data science tool than Julia or Python or R. Another sort of piece of trivia is that if you do series programming in Windows, one of the things that people love about C# and related languages is it has its own equivalent of these dplyr verbs, and it's called LINQ, or language integrated query. And Julia's query package is very much inspired by that version of this. So if you find Julia's syntax a bit weird, that's where it came from. It was inherited from LINQ, which has been very successful in its own domain. So that was a kind of a tangent, but I just want to frame this discussion, what we're learning here with these dplyr verbs, as not being specific to an R package or even R itself, but it's in fact much broader than that. Okay, so now we can pick up where we left off. I want to back up a little bit so we have a context from the last few things we talked about last time. But I think we're probably a complete group at this point. So I want to introduce you to my new friend. So let me get it so that I can actually see myself. So this is Bruno. Can you say hi, everyone, Bruno? Can you say hi? He doesn't know where the camera is. It's right here. Right here. Oh. So we just got Bruno a couple of days ago. He's 8 weeks old. I'm glad you like him. He's pretty much the cutest thing I've ever seen. He's been really still right now. He's extra cute when he yawns. If we're lucky, he'll yawn in a second. There we go. It looks like it was on demand. He's not trained though. That was just luck. So I'm trying to show my school spirit by naming my dog after the school mascot. But he does have some brown in his face, so I think it works out. Do you like the name Bruno? I think he's sleepy. Okay, we're gonna go be held by someone else. Okay. All right. I'm glad y'all enjoyed that. He's been a lot of fun. I don't know if you've ever had a new puppy, but it's a lot of work, but also fun. Okay, so yeah, so let's back up a little bit, as I said, and then we'll take it from there. So we were talking about tibbles last time. And we encountered them in the context of performing a grouping operation, because as we said, when you group by a particular factor variable, you're going to have what sort of looks like the original data frame back again. It's printed here exactly the same as the original data frame, except for this little indication up here that it has in fact been grouped. So it's been stored as a data structure which contains information about this grouping action that happened when this particular operation was performed. And that's important because then if you apply another operation subsequently that is group aware, it will be able to behave accordingly. For example, the summarize function will total up whichever columns in whichever way that you specify on a group by group basis and collect the results. Yeah, that's funny. I put the wink in there. I put the wink in there to try to clarify that. Yes, the comment is I was expecting a famous person from the R world. Yeah, sorry to disappoint. Although I'm not sure which is preferable. Yeah, so there's a R question. Are most dplyr functions group aware? Yes, whenever it makes sense. So for example, if you're selecting columns, it doesn't really, the groups don't really matter. It's gonna be the same operation extracting certain columns, whether you look at the groups or not. So it doesn't really matter. There's not a specific group notion of group awareness yet there. Whereas many of the other functions do have that property. For example, summarize, as we've seen, needs to behave on a group by group basis. You can also imagine arrange should perform its sorting operation within each group. I'll just leave it at that. Whenever it makes sense, the functions are going to be aware of the groups. With regard to these Tibble objects, so the groups data frame is a special case of a Tibble. And the point is that the core data frame supplied by R is just not flexible enough to handle this dplyr manipulation framework. They needed their own data frame type in order to supply extra information that was needed by some of the functions, like the grouped information. And there are other examples, as well as you get farther into using dplyr. And the way this is designed is that the manipulation verbs that can preserve the input do. So select, filter, mutate, and arrange, preserve the class of the input. They preserve what type of data frame it is. So if it's a Tibble, a special dplyr data frame, then that's what it will output. But if you pipe in a regular R data frame, it will output a regular R data frame. And so that's just for consistency, and those four functions, it doesn't matter, they can do either. So they just take the cue from their input. But if you're talking about something like a group by operation, it really has to return a Tibble, as we said, and so it does. And really what you kind of want to do is just keep everything in Tibbles, because that way all the operations can take in the same type and output the same type, and everything stays really smooth. For example, if you import data, which we'll talk about in a while today, then the Tidyverse functions that you would use to do that are going to create Tibbles rather than data frames. Whereas if you use the base R import functions, then you would get, of course, regular data frames and not Tibbles. Okay, so I want to talk about some of the differences. These things aren't crucially important in the way that the understanding these 5 verbs is, but it's still something you want to see in order to appreciate what's going on here. So if you take a column of a data frame, a regular R data frame, as we've seen, that gives you a vector. And so if it happens to be a numeric column, that's going to give you a numeric vector. However, you can convert a data frame to a Tibble using the as_Tibble function, and then perform the same operation and see what happens with that. So if we convert it to a Tibble first and then do the same thing, select the 4th column and then inspect the class, what we'll see is that it is still a Tibble. So it was a Tibble before. If we take out this indexing operation, we're going to see that we get exactly the same result here as we had a second ago. So in other words, even the subsetting even the indexing operation of selecting particular column is going to preserve the data type. So you can see how this prints here. It's just like a regular Tibble, except or a regular data frame, except it happens to be one column because we just selected one column. Okay, but the reason you would want to do this is that the tidyverse functions do require data frames as input. So you would not be able to pipe this one column out using using a regular data frame and then pipe it into a dplyr function, right? It would say this is a vector, not a data frame. There's a problem with that. Yeah, so you can still access the numeric vector just using the $, or as we learned last time, the pull function, which works very similarly, pull of murders, comma, population. But if you index in this way, you will get the data frame back. Another thing that's kind of nice is that you get an error if you try to access a variable that isn't there. So if there's no capital P population vector, so this is a typo that's been made, and regular R just returns null there. And that can be a little hazardous because you know that value might be returned and passed down the line in a computation, and you wouldn't find the bug until later. So to be helpful, the Tibble returns a warning message or prints a warning message. It still returns null, so that it ultimately behaves the same, but it gives you a clue where your problem is. Another thing that's really nice about Tibbles is it's not constrained in terms of the types. So for example, a function in R is a more sophisticated type of object than just a string or a number or something like that. And you're going to, if you want, in a Tibble, be able to store a column which contains functions in it. So you can't do this with a regular data frame. But you can see, we used as an ID column 1, 2, and 3, and then we have actually a column of functions here, which is pretty funky, but this is just fine in Tibble. So it's handy if you want to manipulate things that are more complicated using the kind of tabular data manipulation framework, right? Usually you wouldn't do data analysis with functions sitting as entries in your data frame, but it's still nice to have that flexibility. If you just like dplyr and you like manipulating objects using tabular manipulations. Okay, so as we said a minute ago, the group by function returns a grouped Tibble. So this is a special kind of Tibble, and it stores additional information about which rows are in which groups. So as we also said, the summarize function is group aware, and we experimented with that to see what that looked like. And as we just demonstrated here, although we didn't mention it, you can create a Tibble by using the Tibble function in place of data frame. Otherwise, it looks the same. Instead of data.frame, you put Tibble, and that's going to allow you to construct the data frame. So for example, if we want to construct this little data frame, you see it written down somewhere in a paper in like some kind of table, and you don't want to, the easiest thing to do is just going to be to transcribe it by hand. You can do something like this, Tibble of, and then put the headers here to the left of the equal sign, and then each column should be specified as an R vector. So that's obtained by concatenating entries like this. Yeah, and then as we've also demonstrated, you can use as_Tibble to convert a regular data frame to a Tibble. Okay, so another reminder, when we talk about pipes, the real advantage of using the pipe is not having to rename things. So here's an example where every time you perform an operation, you're having to think up a new name to store the output to so that you can use it in the next computation. And pipes allow you to do that in a cleaner way, as we've seen several times, by taking out all of those intermediate assignments. So the same calculation, really the same operations line by line are being performed here, but in a pipe style instead of a line by line variable assignment style. All right, so you see we get the same result either way. So one of the weaknesses of this setup that you might have noticed that we're now going to figure out how to handle is that each of these functions takes a data frame as its first argument. But what if we want to access a component of the data frame? So for example, let's say we want to access the rate column, and so there is the pull function for this, but there could always be something that there isn't a function for. You don't always count on there being an available function all the time. So what if we wanted to access the rate column without using the pull function? We need a name for the data frame that's coming in. It doesn't have one because that's the whole point, to avoid having to do that. But then we actually want to refer to it in order to say what data frame we're pulling the rate column from. We want to say something $rate. And the dot operator is the key idea for this, or the piece of syntax that's been appropriated by the Magrittr package for this idea. So we could perform the same operation in the following way. So we'll look at this line by line. So this is the same. We filter the murders data frame on so that we only get the rows for which the region is south. And then we create a rate column. And then if we want to extract just the rate column, what we do is we put the decimal point here, the dot, $rate. And when Magrittr sees this, remember, it's consuming this whole thing as an expression. And so it sees a dot, which is, as we said in R, just another letter. So it sees this identifier, then the $, and then the rate identifier. And then it's like, okay, well, dot is a special thing for me. I know what to do with this. I'm going to replace it with the output from the previous pipe. So all this stuff gets evaluated, and then it gets replaced where the dot is here. So it's kind of like dplyr is doing this. It's copying all this stuff and then putting that stuff in parentheses like this. Okay, so that's how the dot operator works. Oops, sorry, I should delete it here. So that's how the dot operator works. It's a name for the data frame that is coming in from the left of the pipe in case you need to refer to it rather than just taking it implicitly as the first argument of whatever function call is there. So just to illustrate this point, I'll show you a much simpler example. Let's say we want to square 3, and we're not content to do it in the straightforward way of just doing 3 to the second like that. Let's say we want to do it with a pipe, and we want to refer to the 3 that gets piped in here. Instead of defining a new function that squares its argument, we just want to sort of put that in really concise notation like this. And so this dot says, okay, what is coming in? And what's coming in is a 3. So this dot gets replaced by a 3, and that's how you get 9. So if you're used to other languages, this is kind of just anonymous function syntax, but it's not an R anonymous function. It's specific to the Magrittr package. You need the pipe in order for it to see a dot and interpret it in this way. Okay, and we covered the dot here because it's going to be necessary in this next section. So the next section is we're going to talk about an important operation that we'll often need to perform, and we're going to need the dot at some point. So you'll see how that goes. So the Tidyverse functions know how to interpret grouped tibbles, as we've seen. To facilitate stringing commands through the pipe, they always return data frames, and that way whatever comes out of one can go into the other without much ado. However, not all functions that we're going to want to deal with are in the Tidyverse. Plenty of people write other functions for R that don't use the Tidyverse, and all the base R packages, or sorry, all of the base R functions as well are going to not be particularly designed to handle Tidyverse operations. And so they're not going to be aware of groups, for example. So we saw this earlier, and we said we're going to come back to a better way to do this. We talked about the Quantile function, and that's a base R function. We don't want to have to recreate a new Quantile function in dplyr. We want a way to use the old one and kind of boost it up so that it can handle this dplyr framework in a smooth way. And the function which does that is called do. So the do function can wrap another function call and make it more sensitive to the way that things are structured in dplyr. So let's look at a specific example of that. Okay, so here was the example from earlier where we said, let's produce a column called range out of the heights data set, and let's return the minimum, in other words, the 0 quantile, the median, in other words, the 0.5 quantile, and the maximum. And we ran it, and we got this, which isn't quite what we wanted. We did get a column, so that's good, but we decided that it would be better to have separate columns, one for min, one for median, one for max, because this way you have to remember the positions. You'd have to get the 64.98, for example, you'd have to index with a 2, and that's not very transparent compared to writing, you know, $median or something along those lines, or pull of median. So the do function fixes this. So let's see what that looks like. So first of all, we do have to make sure that our function that we compute the summaries with is Tidyverse aware. So we're going to write a function called mySummary, and it's going to consume a data frame as its input. And then what it's going to do is extract the height column and then compute the quantiles of that column for each of these specified quantile values. So again, min, median, and maximum. It's going to store that as a variable called x, and then it's going to create a tibble which has min, median, and maximum as its 3 columns. So we extract those 3 values here. So we are still having an index 1, 2, and 3, but we're doing it in the definition of the function, so it's only once. So later we'll be able to access this data using the median word or the max word instead of remembering these indices. Okay, so now we've got this dplyr aware thing, and we can try to perform a computation where we perform our summary after grouping. And what we see is that it doesn't work. There's no grouping action here. So it returns something, it's fine, but it seems to have completely ignored this line where we grouped by sex. It's got everything grouped into one big data frame. Okay, and the reason that there's a problem here is that even though we wrote this function to return a tibble, it's still not dplyr aware. It doesn't have enough hooks to kind of reach in and see everything it needs to see within the dplyr package. So what we're going to do is just wrap the mySummary function call in a do call. So we're going to call the do function, and then inside of that, we'll call our custom function. And this just kind of puts some dressing around that function to make it behave appropriately. And we're going to see that that's going to work. Okay, so I just want to pause and ask a question here. So why did we need the dot? So what would have happened if we had not put the dot and just omitted it? You know, because this data frame's coming in, you know, maybe it should work just fine without the dot. It doesn't work though, and what happens? Okay, so several folks with good answers here, some of them elucidating various aspects of the problem. So yeah, so I'll start with this one. So if we didn't have the dot, what the pipe operator would have done is it would have said, okay, I'll evaluate all this stuff, and then I'm going to pipe that into this function call. And so again, we're pretending the dot's not there. I'm going to pipe that into this function call, and it sees this do function call, and it's going to try to slot all of this stuff in the first position of that function call, like that. And that's not what you want. You want to put it in here. So what's going on is that we need the data frame to go into this expression at a different position than the first argument of the outermost function call in the expression. So the first parentheses here, that's the outermost function call. And it's going to try to insert right there where the cursor is. So that's no good. We've got to move it to a different spot, and the dot is how we do that. And the reason that you get this particular error that you do if you omit the dot is it actually doesn't even get that far. It tries to evaluate mySummary with no arguments, and that throws the error. But even if you defined a no argument version of mySummary, you would still get an error from the fact that you've got something weird in this first position for the do function. Okay, so let's move on. Next, I want to briefly introduce the per package. And basically the idea here, or kind of the core functionality that we're going to discuss, is a replacement for the sapply function. So sapply is fine, but it's a little inconsistent about types sometimes. You don't always know that you're getting the type out that you want. So the per package is going to be more consistent. You're going to be able to control the way that this operation is being performed in a tighter way. To elaborate on the point, we might expect a numeric result from a line of code, but sapply might convert a result to a character. For example, one of the values that you're applying your function to might return a character for some reason, you know, because some function internally couldn't handle that particular input and change the type. And then all of a sudden the entire output vector, because they all have to be the same type, they all get coerced into characters. And now you have a whole column of data that is not the type you expect. And many operations that you might try to perform with it are going to go sideways on you. So per functions, by contrast, don't do this. You tell it what type you want, and it will return an error if it has a problem doing that. So again, it's going to be a problem either way, but it's going to tell you what the problem is quickly with the per version, instead of requiring you to kind of backtrace and work your way back from some downstream error that was thrown. Also, the names are a little bit more evocative. I think sapply, you need to learn that vocabulary in R to know what that means. I don't know how you would guess what that means otherwise. Whereas in per, the names are more evocative of what you see in other languages. So here's the same operation being performed as we did it up there. So we're gonna, instead of sapply, we're gonna use the name map, and we're taking the same argument. So we start with n, which stores the values 1 to 25. So that's what we did in the previous example, and then reiterated that here. And then in another language, you would also use the term map for this. So this just means applying a function entry by entry. And then when we apply compute SN, it's going to take this function and apply it to each one of these elements 1 to 25, and it's going to return a list. So map always returns a list, and you can tell that here because it's printed differently. Map applies the function that is the second argument to each entry in the first argument, and then returns a list as a result. So it will not use some other data type here, no matter what the data type of the input is. It's going to be consistent. So if we want a numeric vector instead, we can do map underscore DBL, like map double, and that's going to output a numeric vector. So that's probably what we want in this case. So if we use map underscore double, we get the desired type. There are also versions for other data types, like logicals are LGL and characters are CHR. So in each case, it's map underscore and then a 3-letter abbreviation for the type that you want. Okay, so I want to field several questions here. There were a couple questions that had come in that I was batching, and then there was a question here now about this. So what types can the first argument be? Anything that R can iterate over. So it's not trying to be restrictive on what you can put into it. It's being restrictive on what you get out. So that's kind of an ideal for a function. You kind of throw whatever in like a wood chipper, and what comes out is consistent, and you know what you can do with it and what you can't. So you can, in this case, for example, we put a vector in and we got a list out. So when we used map without the underscore and type specification, that always returns a list, and we can always bank on that regardless of what goes into it. So if we put a dot in a pipe expression, so one of the expressions in a sequence of pipes, it will not attempt to pipe in the usual way. That's correct. It will only supply the argument at the position of the dot. Okay, so one of these map types, which is particularly handy when you're in the Tidyverse, is map underscore df, because that will always return a data frame regardless, again, of what goes in. So if we do map underscore df with these same arguments, well, okay, it didn't work. And let's think about why it didn't work. This was a vector, and we applied a function to each element of that vector. So we get a number out for each of them. So that's what we saw before. If you do DBL, that's what you get. So we get numbers there. And if you want to convert that to a data frame, what R is saying is there should be a name for the column in the output. We can just kind of mess with the function a little bit to get that to work. So again, we store the values 1 to n in a vector called x, except this time, instead of returning just a vector, we're going to return a tibble that just labels that vector as sum. So now when we apply the compute SN function and map that over the values 1 to n, we're going to get what we want. So it knows what to call it now. It has no trouble outputting a data frame. And so we get what basically amounts to a vector, but it's in the form of a tibble rather than being just a plain vector, right? So that's nice if you want to pipe it into another function that expects a data frame. You've got one. Okay, so this was a very, very brief introduction to the per package. There's a lot more there that we aren't going to go over now. If you do want to look into it, there's a link here for a place to look. Okay, I want to give you a couple more functions that are super handy, especially this first one, I would say, because it's quite a mess to do this without such a piece of functionality. So we talked about the if-else function, and the nice thing about this function as opposed to using an if statement is that it's vectorized. So you can apply it to a lot of values at once if they're stored in a vector or a similar data structure. But the problem with if-else, especially used in this vectorized way, is that sometimes you have more than 2 conditions. It's not just okay, if in this one case we go one direction, in some other case we go a separate direction, you might want to check three possible directions, like positive, negative, and zero, for example. And you can do that by branching if statements or branching if else functions, but your code becomes unclear. It's arbitrary how you split up the conditions at the top level, and it becomes difficult to parse just looking at the code and trying to remember, wait, what was I doing here? Or what was this person doing when they wrote this code? So what we'll introduce here is a function called case when, which belongs to the tidyverse, and it provides an alternative to have more than just those two cases. So it works very similarly to if else, except again, it can handle as many cases as you want here. So for example, let's say I want to convert the entries of a vector to a word which just says, are they positive, negative, or zero? So what I can do is I can say case when x is negative, return positive. And we use a tilde here. So remember, this is creating a formula. And a formula in R is just, you can think of it as kind of a held piece of code. So when R sees this, x less than 0, tilde negative, it sees the tilde, and it's like, okay, this is a formula. I'm not going to evaluate anything. I don't care what x is. I'm just going to hold this kind of in my hand without doing any more stuff to it. And then the case when function is going to be responsible for consuming that piece of code and doing something appropriate with it. So in any case, we put our first case like this. We put the condition and then a tilde and then the value that should be returned in that case. And then we can just list as many of these as we want. So we just list 3 here. It's reasonable to put true as your last condition because the idea is it should be exhaustive. It should be whatever value is there originally, one of the conditions gets met and then something gets returned. So we don't really have to check whether it's equal to 0 here. If it's not less and it's not more, it's definitely 0. So we can just say true for this last condition. So in any case, we run this, we get exactly what we expect. It says negative, negative, 0, positive, positive, which is what you would think. So I'll show you a kind of bigger example to see what this looks like in the wild. So suppose that we wanted to introduce our own regional categories. Let's say New England, West Coast, South, which we'll inherit from the original data frame, and then everything else we'll just call other, right? So it's a different way of splitting up the regions than the one we were given. And there are various ways to do this. One particularly clean way is to use the case when function. So what we're doing is we're creating a new column called group, which is going to say what group it is based on this particular schema. And for each row, what's happening is the abbreviation value is being checked for membership in this particular manually entered vector of New England states. And if so, if that evaluates to true, then the value New England is going to be returned for that particular row. All right, same thing for the West Coast. And if that doesn't work, then if the region is equal to South, then we just return that same value. So we're piggybacking off of the southern delineation made in the original data frame. And then, as we said, if none of these conditions meet, then we just return the value other. All right, and then let's say we want to check the rate for these regions. All right, so we'll just group by that newly created group variable and then summarize just exactly as we have been before with other delineations. So you'll have, New England is quite a bit lower here than the other ones, and that becomes more clear than when it was lumped in with other states in the Northeast. So because remember in the original data frame, Northeast was one of those categories in that factor variable. Okay, so here's one more. This is the between function. And this does, again, what you would think. There's nothing super fancy here. It's just kind of convenient. So suppose that we have these values and we want to check for each one whether it's between 0 and 1. So you could do this with a ampersand, but you have to write x twice. You have to say x greater than or equal to a and x less than or equal to b. And it's sort of nicer if you can only write x once, because that way, if you go back to change the name or insert an expression here, you don't have to paste it in both places, maybe accidentally leave one of them, and now you've got a problem. Calculation is wrong and you don't know it. So we want to kind of clean this up. This would be the straightforward way to do it. And this is the tidyverse way to do it. We just use the between function. So between of x, comma a, comma b returns exactly the same thing. It's doing the same computation. It's just a little bit cleaner because now we only have x applied once. And it's also more transparent. If you see this, you immediately know, regardless of whether you know R, someone is checking whether something is between some stuff. And then maybe you have to figure out more details after that. But the between part is kind of slapping you in the face. Here, if you're anything like me, you have to parse this out. It takes a good 5 seconds, even when you're used to it, to check, yeah, this actually is checking that X is between A and B, right? Whereas here it's much more clear. Okay, so I want to give you an exercise. I'll give you a few minutes to try to work it out, just to practice with some of these things. So there's a common function in scientific computing called clamp. And the idea is you want to make sure you're outputting values that are strictly between two specified values, like let's say 0 and 1 in this case, but you don't want to mess with anything in between. So it should leave the input untouched if it's between those two values, and it should saturate either at 0 down here. So you can see in this function, if you move this around, it's returning 0 until you hit 0, and then it's returning the exact same value that was plugged in, and then it saturates at 1. So if anything bigger than 1, it returns 1. So the goal is to write an R function whose graph looks like this. And I've written this little test here for you to check that your output for that particular X that we typed in above, you want to check that it returns this vector as output. So when you run this cell, it should say true if you've put your function here in a correct way. All right, so several folks are contributing their solution here as the time expires. So it's enough code. It's hard for me to parse each one, but you were able to run them and run the test. So I'm assuming that most of these are accurate. Yeah, so several examples here. Most folks are using case when. I agree that that's the cleanest way to do it. So for example, we can say if X is negative, then return 0. If X is positive and also less than 1, return X. That's just fine. We could use the between function to clean this up a little bit, but this is completely fine as well. This is more of a kind of base R way to do it. And then otherwise, then we know it's bigger than 1. We can just return 1. That works. Yeah, so here's another one using between. So if X is between 0 and 1, return X. If it's negative, return 0. If it's positive, return 1. Yep, that works. Okay, so here's what I have. I have a couple of solutions. So one is very similar to the examples that were given here. So I just checked if it's negative or if it's bigger than 1, saturate, and otherwise just return the X value that was plugged in. So I used a true here to kind of avoid having to use the between function, but it's all good. If we run this, then it returns true. So this worked out. Here's another solution to kind of illustrate the point of why case when is nice. If we want to use it with, if we want to do it with if else, we can, but we need to nest. So for example, we can check, is X between 0 and 1? If so, return X. But then if not, you've got to do different stuff depending on what the input is. So we need another if else here. And that's kind of wonky. You know, you read this, there are 2 if else's. You got to parse it out. It's not as straightforward to read through and make sure you know exactly what's going on. However, it does work. Okay, so I want to just briefly mention some data stuff here in the last few minutes of class. So some information about importing data, just so that it's on record in the class. It's very important, but it does separate from some of the other concerns, the data manipulation and visualization that we've talked about. So it's fine, I think, to just let folks read this in specific detail as needed. So this is really intended as an orientation. So we have been using data sets that are already stored as R objects, either pulled in from a library where someone else has prepared it as an R package, or just built right into the language. Either way, we're able to grab it as an R object, no conversion necessary. However, of course, if you're working for a company doing some research in a lab, they're going to be pulling this data in from some interesting source, and it's not going to be as an R object the vast majority of the time. It's going to be stored in some file that you get handed. Maybe it's, you know, on the internet, you have to download it and you're given some kind of password or something. Maybe someone hands you a thumb drive, but it's going to be a file and you're going to have to get it from your file system into your R session. So the simplest, probably most ubiquitous way of doing this is something called a comma separated value file. So we've talked about this a little bit. Here's what it looks like. You'll have a plain text file on your computer. So it's something you can open in any text editor and just look at. And it will have different lines like this, each one containing a row, and each row is going to have its entries separated by commas. So that's why comma separated values. And you can then take this file, and so for one thing, you can create it. If you make a data frame and you want to share it with someone else, you can write it out to your hard drive in this format and then give that to someone else. And then that person can then take that file and bring it into their R session. And it looks something like this. So this is an example of downloading it from the internet. So I like to remember, I just have this stashed away in memory because it's often handy to be able to grab a CSV from the internet just to make sure something's working right or whatever. And the iris-dataset link on Bitly is, as you would guess, the iris CSV file. So I'm going to download that file using the download.file function. That's the simplest way to get something on your machine quickly. And I'm going to use the read_CSV function from the readr Tidyverse package. And that's going to pull in the iris data frame. Of course, that's exactly the same as the one built into R because it's the same data set. But the point is we got it in a different way. So we could get other CSV files in this way that aren't built into the language. And the reason this worked, and this is important because it is easy to get mixed up on this, the reason this worked is that when you use the download.file function, by default, it puts the file that is being downloaded into your current working directory. So that's kind of where you are in your computer's system of folders. And readr is also going to read from your current working directory. So we can kind of get some insight into what's going on with this using the get working directory function, getwd, as well as the list files functions. We can see what's going on. So we're in our home/Jovian directory, and we have these various files, who knows what they are, sitting in there. So this /home/Jovian thing, this is it's called the path of our current working directory. And incidentally, this Jovian, it's a sci-fi reference. It means someone from Jupiter, and that's riffing on the name Jupiter, which is the technology that all of these code cells that we're using in Prismia are built on. This is called the path of the current working directory. And the path of a file you can think of as a list of instructions on what folders to open up in order to find the file in order. So this, if we were starting at it's called the root directory, the kind of very top level in our computer's file system, we would open the home directory and then the Jovian directory, and then we would be right here where these files are sitting and where our R session is currently operating. If you have a slash at the beginning, that's telling you that your path is an absolute path. It's telling you where on your computer exactly to find that file. If you do not have a slash at the beginning, that's called a relative path. And that's telling you where to find a file relative to where you are now. So you have to be in the correct location initially in order to find a file that's specified by its relative path. And you would think that that is worse because it gives an opportunity for something to go wrong, whereas an absolute path would seem to be safer. But if you think about how people tend to use their files, actually the opposite is true. If you were to use an absolute path, and then you moved your whole directory that has all of your project files for the analysis you're performing, then all of a sudden, all of the paths which specify where your data is would no longer be valid. They would need to all be changed to update to refer to the new location where you've removed these files to. Whereas if you put everything in one folder and then use relative files, as long as the whole folder directory stays intact, you can move it wherever you want on your system or zip it and send it to someone else, and everything is still going to work just fine because it's not going to be sort of trying to look outside of that folder and use an absolute path that might have something like your username hard-coded into it. Obviously, that's not going to work on someone else's machine. But if you use relative paths with no slash at the beginning, then it's going to work fine. So here's an example just to be explicit about that of how you could do this in R. You could also use your operating system to perform all of these operations. So you don't necessarily need to learn these commands, but just to give you a sense. So let's say We want to create a new directory for our project and call it flowers. And then we want to change directory into that flowers directory that we just created. So we'll use the setwd command. Then we want to create a file called flowers.r. That's where we're going to put our R code to perform our analysis. And then let's say we want to put our data in there in a directory called data. So we first create that directory, and then we previously already downloaded this file. So instead of downloading it again, let's just move it from where it was before to the data directory. And you'll notice I use these 2 dots here. This means go back up one directory. So I change directory into the flowers directory, so I have to step back out in order to get the iris.csv file. This is just telling where to grab the file. It's gonna, my current working directory is gonna be where it was the last time I set it. So you can see that here. If I pull up a code cell and do get working directory, I'm still in my flowers directory from when I set it here. And if we want to get a clearer picture of what's going on, there's a handy function called dir_tree that's available in a package called FS. So this package is supplying file system utilities that provide an alternative to these file system utilities that come with the base language. And there are various advantages. You don't really need this package, so I would actually encourage you not to run this now, but you can if you want. Either way, this is what the output looks like. So it produces this nice tree visualization of your file system. So there are these files that we saw before, whatever, and then there is this flowers directory that has a data directory within it containing our data. And then we also have a flowers.r script where if we wanted, we could start recording our R code to perform our analysis on this data. And you'll see this in not just in R, there are a lot of different environments where you can get functions that produce this kind of tree shape to illustrate what's going on in your file system. And by the way, all of these other things, environment.yaml, post build, these are all things that are just part of how we specify to Binder what packages we want installed. So if you look in there, it's going to have some information about DS Labs because our Binder servers are coming with DS Labs pre-installed. As you'll notice, we've been able to use library DS Labs without installing it, every day. I did that just to make this class more convenient. In any case, you can ignore that stuff. It's not going to be part of any local installation of R that you might be running. Okay, so the flowers.r file can contain a line like read_csv data/iris.csv. And when you run that script, it's going to use as the working directory the directory where you're running it from. So where the flowers.r package is, or sorry, the flowers.r script. So it's going to reach into the data directory from that directory. So it's kind of operating within here. And it's like, okay, this is a relative path. There's no slash at the beginning. That means I need to look inside this folder and it's going to find it right there. And then I need to find the file within that folder, and that's going to work fine. And then you can take this whole flowers directory and move it somewhere else or send it to somebody, and it's all good. Okay, so just a couple more points. There is a readXL package with a function called read_XL that does a similar thing as the read CSV, except it works for Excel files. So XLSX files or XLS files, if you're used to working with those, you can integrate those very nicely with R. This is an advantage of using a popular language like R. Pretty much any data format with any real currency out there, someone will have felt the need to write a reader for R so that you can pull that data into R conveniently from whatever file format. I'll share one example of a file format that you might not have heard of that I think you should have, and you can consider using it in certain situations where it would be worth the trade-offs. So there's something called a Parquet file, which is a relatively new thing compared to some of these other file formats. It's an alternative to them, and it's not human readable. So if you try to open it up on your machine, it's going to look like gibberish. However, basically in every other way, it's going to be advantageous relative to CSV files. So for example, it tries to do some smart stuff to represent the data more compactly. And that's going to enable you to read and write files faster and store them with a much smaller footprint. So for example, I switched to using Parquet from CSV in a particular project I was working on because I was having some issues with the size of the file. It was enormous. and we were able to shrink it down to a much smaller size, literally just by converting it to the Parquet format. You also don't have parsing issues with Parquet. So it's a standard that's uniform, whereas CSV files have lots of different discrepancies in how people handle things like spaces and new lines within text entries and commas within text entries, all of that kind of stuff. It gets processed differently by different readers, and you can end up having some glitches with that. Whereas for Parquet files, it's standardized, and it's going to be a much more consistent experience from one environment to another. And that's all I have for today. So next time, we're going to introduce ggplot2, and we're going to start talking about the grammar of data visualization, and that's going to take up both of the last 2 days of this class.